Okay, we only have 1 hour today, so I'm not going to wait. We have videos. So for the design for gears, one thing we worry about is whether the teeth or tooth is going to carry the load. So this is one illustration of the tooth from a straight gear. Over here you can see the geometry is not straight. It's not a straight geometry. So if you truly want to apply some force and then study the stress distribution inside, definitely doable. However, it's not easy because there's no exact equation for this. The geometry can be changing in many different kinds of parameters. So you probably need to use software to estimate the stress, concentration, and so on. So there's one way to analyze, or you can say estimate the stress distribution inside the tooth is by this method. So there is someone called Lewis defined this Lewis factor. Okay, so what he did was he simplified this complex geometry into a rectangular beam. So consider the tooth as a beam. Simplify it as a rectangular beam. And see if you can use it to estimate the stress. So if this rounded shape tooth can be reduced to a beam, what would be the geometry? So what he did was he decided to find a point right here. So remember we have addendum, dedendum. So this is like the root, the bottom of the dedendum. So it's almost like the L is the length of the tooth from the root to the very tip, very top. Okay, so why do we study the force applied to here? Because the force doesn't really apply to here. The force actually rolls from the edge from one point to another because gears have this conjugate motion. So this, you can say this is a worst case analysis. When the contact point is right at the tip, and if the same amount of force is being transferred from the other side to this side of the gear, then the tooth probably is carrying the most load because the force is all the way at the tip of the tooth. So it's basically providing the greatest bending moment to the tooth. So for this model, the applied force is basically right at the tip. And due to geometry, there is a parameter called x. So you can see right here, they draw a straight line from the top point to this, you can take the neck, the point at the neck, and consider this as 90 degree, and then find this like another point at the middle of the neck. Okay, and from geometry they call this dimension x. So that x will be used later on for dimensionless analysis. Okay, so once you have the length, they treat this beam as the same length. Okay, so what is f? So basically, for every gear, there's a thickness of the gear. So this is F. Okay, this is F. So it's the width of the face. So what does the gray area represent? This is basically showing the cross section. So actually, it's these two lines doesn't belong to the geometry. This is just to draw how the cross section look like. Because sometimes people do this. What does this mean? This means this is a circular beam. This is just representing the geometry of the cross section. So this is a rectangular beam. Okay. So it's telling you, basically trying to tell you the thickness into the board is that. And how about T? So T is right here. So it's like the width of the neck. The width of the neck. So that would be T. So the geometry right there is a simplified version of the tooth right here. It's not the exact same shape, but size-wise, it's similar. Okay? And there's a transverse force being applied from the other side of the gear. So why does the original force come into the T with an angle? Because you know, for two gears, if I'm drawing the pitch circles of two gears, we always have this pressure angle right here, right? Pressure line of pressure or pressure line. It's just basically telling you if there's a tooth right here and another tooth right there, and the force basically goes along this angle. Okay? So the force coming from the other side has an angle, and this angle basically is a pressure angle. So you can take a cosine of it, you can have the transverse external force. Do we need to worry about the vertical one, the radial direction? Not much, because that one doesn't cause bending, and we only worry about the bending, the normal stress due to bending, because we worry whether the tooth is gonna break. So we only study the bending caused by the transverse force. So once we have that, remember we have the model stress equals to MC over I, right? So C right here. So here I have another file. Yes. So I already took some notes. How do you compute I over C? Okay, and basically C is half of T, and so I over C is half of T. So what would be the I? I think it's 12 over, on top it should be FT cubed over 12. So at the end you will have FT squared, and you have 6 right here. Right, exactly like what I did over there. So when you plug it in at the end, so how do you compute the moment? So moment is going to be the transverse force times the length L. That's why you have a WTL right there. Okay? So the stress can be estimated as that value. Transverse force times, so related to transverse force, the length of the tooth, the width of the tooth, and the width along this direction. So basically some geometrical information. Okay? And to convert this equation into a more general form. So this person Lewis defines so-called the Lewis form factor. So it's a factor that provides some kind of dimensionless geometry. Okay. So in order to have a nicer equation at the end, and in order to form define this Lewis form factor, at the beginning you need to rewrite the equation in a certain way. So this is just for better derivation or nicer representation at the end. So you need to do this. T over 2. So this is basically by the geometry. So T over 2 is like here, 1/2 over x. So this geometry is similar to this one. So this edge over this edge will be similar to this longer edge to the width right here. No, similar geometry actually this one. So L over T over 2. Okay, so this triangle has similar shape as this triangle. Okay, so again, this is T over 2 over x equals to L over T over 2. Using the similarity of the triangles, you have this equation. And then you can rearrange it. At the end, you have something called x equals to t squared over 4L. Or you can describe L in the form of x. Okay, once you have those, you can plug it into the equation right here. So you can replace L by that one. So at the end, there's no more L. Once you do that, there's still this one will be replaced by x. So replace L and also replace all terms that is related to L. Okay, so by plugging these two equations into the following form. So at the end, you end up with something like this. There's no more L, and even no more T. So what's the benefit of this? The advantage is that you don't really need to measure L and T anymore. Okay, so you will be you will be designing the gears in this Lewis form factor. So it's like a dimensionless factor that represents the geometry. So so this is a ratio of two different length dimensions. So x basically is a artificial dimension that it was created at the beginning, and p is basically the circular pitch. Okay, so y is the ratio in this way. So if you plug in right here, at the end you will see some numbers will be replaced, then the final form looks like this. So what does this mean? Stress usually is force over area. So this is still our force. So how about this area? So this is more like a equivalent area, something like that. So F still is the width right here, the thickness right here. But when you multiply it's like you're trying to compute the stress area. You have this, and you need to kind of compute some dimension on this direction. So over here, you basically multiply the circular pitch times this dimensionless factor y. And by derivation, it tells you that's basically the same stress. Okay? Or if you don't like P, if you take a look at this one, it's gonna be like WT over F times 2/3 of X. 2/3 of X, right? Because you can get rid of P from on top and bottom. So this is like F times certain amount of X. Certain amount, like 2/3 of X. Okay. So that's the interesting part of this Lewis form factor. So it's a shape factor. Okay. So once we have that, what can we do later on? We can define this. We have the small case parameters and the capital case parameters. So what are those? Why do we do that? Because in gear equations from the last time, we have small case equations and we also have the large case equations. So over here we have capital P and small p. Okay, so capital P is the diametral pitch. So it's the ratio of number of teeth over the diameter of the pitch circle. Small p is the circular pitch. It's a small distance that represents the distance from one tooth to the other tooth. So for gear calculations, capital P and small p has a relationship like this. When you multiply them together, it equals to pi. So in Lewis form equation, we already have small p equations. Now, due to the capital P equations that was already exist in gears, can we represent this stress equation into the capital P forms? So that's basically what happened. Let's try to plug in the relationship between the capital P and capital Y, the concept of capital P and small p. But over here they use same idea, capital Y and small y. Okay? So if you have the same relationship, but this time they are basically capital Y over pi equals to small y. So it's slightly different. We have capital P and small p multiplying equals to pi. But for the y, it's capital Y over small y equals to pi. If we can do that, then at the end, you come out with this equation as okay, you can have this equation after the derivation over there. Then you can replace the equation that we had earlier, because in the previous page we have this one equals to WT over F and then small p and y. So small p and y can be replaced by capital P and capital Y. Then you have this equation, capital P and capital Y. So why do we care about this? Because when you estimate your stress, sometimes you can use the equation, but if at the moment you have no idea about your small p, you would like to use capital P, then directly you can have this capital P version of equation. Okay, so basically it really depends on what parameter you have right away, or based in the process of your design, what parameter was your like a parameter you use more often. Then there are corresponding design equations that you can use. Okay, now once we have this Lewis equation, we can use it to estimate the stress inside the tooth. However, start from the beginning, we already know this is basically some kind of estimation. It's not always accurate unless you really use some software or do experiments to measure the stress. So the textbook started to provide tables and general equations and a lot of correction parameters to the Lewis form equation. Now, I will quickly go through those for your future reference. So here, the book already provide the capital Y in different numbers of t. Okay, and this is basically for pressure angle 20 degree, so-called the full depth teeth. So the entire teeth has a complete depth. Okay, and this is for diametral pitch equals to 1, and it's rotating in a plank. So from here, from this parameters right here, I got it from the textbook. It's telling us this is why, well, the parameter of capital Y changes in different settings, general settings. Okay, so you cannot just directly use it if you are having different settings. Okay, so in mechanical design, make sure you read carefully on all kinds of tables. Sometimes the table is utilized for certain parameters. Now, we will start to talk about various factors. I will show you how those factors ends up look like in the final equation. So I will quickly jump forward. Let me see. Okay, so this is actually the final form. But what happened is so different from the Lewis stress equation. Yes, it is very different. So over here you can see we can focus on either line of it. Either it's a SI unit or the US unit. That's fine. But let's take a look how many factors will affect the estimation of stress. So WT is still the same thing, the transverse force. There's something called KO. So it's a multiplier right there, and it's related to how much load that is applied to the gear. There's something called KV. So somewhere over there. It's about dynamic. What does it mean? It's related to the speed. So when the gear is rotating in a different speed, it actually generates different levels of stress. So there are some tables for you to, some equations for you to check. KS, somewhere here. So it's about the dimension. So when you design a small gear or a large gear, even though we already use this general equation, a dimensionless approach to form this stress equation. Looks like a general one. However, in different size of gears, there will be changes. So they use this product vector to correct it. Now, capital P basically is the capital P we know, the diametral pitch. Okay. F basically the same F. So the width right here, same F. Kn, load distribution vector. So if for some cases your load is I think it's about the timing. So let me double check. Km, load distribution. Okay, and load distribution. So, it's about the stress distribution on the surface, on the face of the gear, because sometimes the gear has a crown geometry. So, it's fatter at the middle, but thinner from the edge. So, it's the real shape of the gear looks like a crown. Okay? So in fact, the load concentrates at the middle area because it's a fatter area. Okay, so all the equations that we had will not be accurate if the geometry of the tooth has this crown shape. Okay, so that's for the load distribution. Here. Another parameter is called the rim thickness. What's a rim? So if you have a gear that looks like this, looks like a donut. Okay, it looks like a donut. So the hole right at the middle is not a small hole; it's a really large hole. Then it's called a rim. Okay, so the stress that is so you have less support at the middle, at the root of the tooth. So it needs some kind of correction as well. J and capital Y is related to capital Y. So basically, capital Y is our Lewis vector in the capital format. So it basically is a geometrical factor. M is our module. Okay? So those are the parameters. Okay? And all the rest are the same. So usually the factors are just multipliers, like numbers in the scale of 1 or 2. So they are just multipliers. So if you ignore the multipliers and take a look, it's like a capital W times capital P over capital F over J. And or capital W over B and Y. Okay, so B N module has no dimension. Y actually Y has no dimension. So module The module has dimension. Oh yeah. Oh, actually, yes. Y has no dimension. Small y is a ratio of x over p. So small y is dimensionless. Capital Y is x times capital P. So capital P is n over d. So capital P actually has a dimension. So capital Y has dimension. Is it? No, because let's check the unit. Capital Y, capital P is it's a number over length, right? Number over length. Okay, that's capital P. How about capital small y? So small p is pitch. So small p, so this is capital one, this is small. Small p, of course, is the unit of length. Okay? And if you check on y, small y, is in the unit of length over length. So it's like a dimensionless, right? It's a x over p. X has length. So how about capital Y? Capital Y is length. Capital P is number over length. So capital Y has no dimension. Okay? So small y and capital Y, they both has no dimension. So over here, module. Does module has dimension? Module is module has dimension. Module is the dimension in length. Right? So if you go back and check on the gear equation, it's still force over length times no dimension. So it's still force over area. All the other multipliers are just correction factors. Okay, so let's take a look at how each correction factors can be determined. So there's a I think KV was introduced at the beginning. So over here, we find different forms of equations based on different ways of production. So if you build the gear by casting, your equation looks like this. So if you have 0 speed, then K equals to 1. But when the speed starts to increase, the K is greater than 1. So whenever the gear is rotating, your stress increases by a certain amount. And if you build the gear by cutting or milling, then there's a different equation. So which one is good for dynamics? Cut or milling? Because let's say you have a speed of 100. You have a speed of 100. KV for the cutting one It's gonna be 1300 over 1200. So it's 13 over 12 in K. But if you have the same speed for the casted geometry, it's gonna be 700 over 600. So it's greater K. So from here you can see, for gears, the way you produce the gear matters. Okay, cutting and milling. The gears that was cutted or milled has better adaptiveness to speed. You can say that. Okay. There are some other parameters. This is for hopping and shaving, different equations. So hopping is one way to create to manufacture the gear, and shaving is another way. Okay, I actually made some. I found some YouTube videos. So take a look. So this is hopping. Okay, so they have a cutter, a tool right there. The motion is called hopping. Okay? How about this one? Shaving. So that was the tool. It was right there. That's the tool. Like shaving a beard. Okay. So you can Google for more videos. Now, these are just the dynamic parameters in different units. So you convert the equation into different units. That's all. Lewis form equation we already mentioned. This is about contact stress. I'm not covering that, so I'm gonna skip. Okay. I forgot to talk about something called the this is contact stress. This is bending stress. Okay. But I need to talk about the allowable stress. Here, allowable bending stress. So what we had earlier was just to compute how much stress that is being applied in the teeth. But what will be the limit? Is it just yielding strength? So there are also equations for the allowable stress. And there are also correction factors for the allowable stress. So ST is the allowable bending stress. So usually you can use the yielding stress. Y basically it's a different Y. So it's not the same Y. It's a factor about how many cycles. KT is something about temperature. So if your gear gets too hot, the allowable stress changes. KR is about reliability. So it really depends on what's the safety level you're looking for. If you want your gear to be 99% of safety, that means you need to have a very strong gear. Or you have to carry smaller loads. Safety factor, basically SF right here. Okay? So we will quickly go through. I will show you the final design equation. Just put them both together. Let's see. Yep. So actually the textbook shows this. How to compute stress? Okay, here's the general equation. Where to find ways of determining those parameters. it tells you where are the pages. You can turn into those pages and figure out. And this is the allowable stress. So basically, this stress must be smaller than the allowable stress. That's the general design equation for the tube. Okay? So like this. This stress must be smaller than the allowable. So in design of mechanism, in dynamics, in all other courses, they don't care about this. They never talk about whether a tooth can carry a certain amount of load. So only in this course you need to worry about it. Okay? So it's not easy. For gear design, it's not easy. Many factors to consider. Okay? I only have 10 minutes left. Just to give you some additional information. Gear wear, there are two kinds of gear wears. One is bending, so basically breaking the teeth. The other one is surface wear, because we have strong stress concentrated right at the surface. So two objects contact with each other with high pressure, actually there are greater stress concentration right at the surface. Okay? So in this course we haven't talked about surface stress. I didn't introduce it at the beginning of the course. But there are actually models talking about how much stress concentration there will be right at the surface. That's gonna cause issues. And in the entire textbook, actually only gear pairs has this issue. Okay. So there are many different models, and I'm not going to cover them. I just want you to know, if one day you are truly designing gears, you need to know stress concentrated at the contact surface, and there are already design equations. So what does that mean? That means you not for the safety of the gear, you not only need to satisfy this equation so it doesn't break by bending, you also need to worry about surface stress. There's a totally different set of equations. The book gives you really good guidance. So there are contact stress and allowable contact stress. So this value must be smaller than this one as well. And they have, for contact stress, there are different sets of parameters. They are all in the textbook. We have a little time. Let's just quickly take a look at those cases and then we're done. We already covered the dynamic one. So we now can talk about here. This is allowable bending stress. So it's not, you don't directly use the yield restraint. You need to check the table. And you realize it's related to the hardness of the material. Okay, so, and over here you see two different lines. They are grade 1 and grade 2 allowable stresses. So they are like different levels. This depends on what kind of level you're looking for. Why does the grade 1 is lower? Because if you allow lower stress, that means you have better safety. So it's like a higher reliability. And so grade 1 seems to be a choice that you are looking for stronger performance. And whenever you see equations like this, you will know it's determined from regression. What's regression? 回归. So this definitely is something estimated by linear regression. So they must have done some experiments. They realized the allowable bending stress is related to hardness. They have done some experiments. They found some dots right here. They form a linear equation by regression and give you the number here. Okay? So what does that mean? That means to truly determine the general equation between this vector and this vector is very difficult. You don't have enough physical knowledge to form that. So one approach is to use statistical way. So when you are in master's degree, when you work on some research, when you see something like this, okay, that means maybe you can study for the physical equation for it. Or if you are handling different scenarios and you realize whatever you are working on is not on these two lines, that means you can do your own experiments. Maybe you have a grade 3 experiment, and then you can form your own equations. Okay, so this is like a hint for you for your future research. This is this one is for steel, and this one is for a nitride hardened steel, so a stronger steel. Okay, and this is nitriding steel, different levels of hardening. They have chrome at the surface. Okay, so giving you a sense about how the allowable bending stress will be affected. And let's take a look at more parameters. Don't talk about content ones. Okay, geometrical factor. So this factor, J, is not the J that we know. It's not the I and J that we learned in the past. So over here at the bottom is the number of teeth that you are analyzing, and the numbers right here are the number of teeth for the neighboring gear, the mating gear. So this geometrical factor really is related to the number of teeth for the current one and the neighboring one. And let me see what are those. Okay, so whatever you get at the end basically is a factor for J. Okay? And it's only good for the geometry right here. Okay. This is for helical gear. For helical gear, you need to study the J in a different way. Okay? So there's a multiplier for J if you are using helical gears. And it's related to the helical angle, helix angle, and number of teeth. Okay? There are actually more, but like I said, I'm just here to introduce you what people need to worry about in gear design. So now, if in the project you're studying gear design, you can find a textbook, or from our lab we have books, or borrow one from library. You can look into those, or just Google for gear design references. Okay? So I'm not going to cover the whole chapter. That's everything I want to talk about for gears. And today we have attendance check, so please do it. And I think schedule-wise, there are some changes. So we are already here. I am 1 week late. So next week I will talk about varying. So I'm not going to modify the syllabus anymore. So from now on, we basically just cover different chapters of components and tell you what is important for those components. And you guys basically just focus on the project. Okay? I think there's no more homework. Oh, there it is. I should remove it. Why should I need homework? Okay. So I don't think I need to create homeworks anymore because we only cover very little parts. So if I do that, that means I need to modify your score of these. Oh, I didn't do homework for, then no more. We don't need homeworks for components. So I should give you more scores somewhere. Let's do more on attendance. How about 1 point per attendance? Oh, that's great. Is that great? Double the score for attendance. And this one is for the proposal. Proposal is this one is shift to here. The progress report. Let's change the progress report to 9, and this one should be 1. We don't need report here. So that will be totally 100. Okay? Everyone okay? Yeah, so I upgrade the attendance. Is it too much? I think it's a little too much. It's greater than the exam. Maybe 12 for exams. So over here, 0.9, 0.8. Oh yeah, how about this? So it makes more sense. So 24% for the exam, 70% for attendance, 11% for homework. I think it's kind of reasonable. Okay, we'll see. Okay, that's all. Thank you. Bye-bye.